This is a video for AQA Further Pure, second order differential equations 1, homogeneous equations, 1.6, auxiliary equation with imaginary roots. We've already looked at this second order differential equation and seen that the solution starts with forming the auxiliary equation here with a variable m in it. Depending upon the solutions to this quadratic equation, we get different sorts of general solution. If the discriminant b squared minus 4ac is greater than 0, we get two distinct real roots. Let's call those lambda 1 and lambda 2, and in which case we get this as the general solution, a e to the lambda 1x plus b e to the lambda 2x. If we have this b squared minus 4ac is equal to 0, then we get a repeated root, let's call that lambda, and in which case we get a general solution a plus bx e to the lambda x. We're now going to consider what happens if b squared minus 4ac is less than 0, in which case we'll get complex roots here, and we need to look at how that affects the general solution. Okay, so let's look at this example. Notice I've got no dy by dx term, I've got b equals 0, and I start by forming the auxiliary equation. Well, that's going to be a m squared plus c is equal to 0. That's going to give me m squared is equal to minus c over a. And this means that m is going to be imaginary. Let's call that beta. So m is going to be beta I. And I'm going to get plus or minus. So the general solution is going to be of the form y is equal to a e to the beta I x plus b e to the minus beta I x. And if I just rewrite this slightly, I'm going to get y is equal to a e to the I beta x plus b e to the minus I beta x. And now these things look like complex numbers with an argument of beta x. And we can show that this is actually equivalent to y is equal to p cos beta x plus q sine beta x. There's that written up a little bit more neatly for you. There's my auxiliary equation and its roots. So we know that the general solution is this form, and which is equivalent to this form here. Let's examine that last step in a bit more detail. If I'm starting from here, I know that these are my forms for e to the I theta and e to the minus I theta, and so the general solution can be written as a cos beta x plus I sine beta x from the first bit, it's using this, and b cos beta x minus I sine beta x from the second bit, that's using this, and if I pull together the real and imaginary parts, you can see I get these. And all I've done is to rewrite a plus b as some other arbitrary constant p, and I a minus b as some other arbitrary constant q. So how does that work in practice? If we have a look at this differential equation, once again we'll start with the auxiliary equation, m squared plus 36 is equal to 0, which gives me m is plus or minus 6i, and so that gives me a general solution which can be written in the form y is equal to p cos 6x plus q sine 6x. Again, that's just written up tidily. There's your original equation. Here's the roots of the auxiliary equation. And finally, just this result here. And you can move straight from the roots of the auxiliary equation to quoting this as your general solution. Okay, let's have a look at a plot for this general solution. Here it is with P and Q equal to 1. And one of the things you should know from elsewhere is that we can write a combination of coses and sines of the same angle. We can rewrite that as r sine, in this case 6x, plus alpha. And r represents the amplitude, alpha represents the phase, and that's a translation parallel to the x-axis for the sine wave, and this relates to the frequency. And in this example, this tells us that this is going to oscillate 6 times over the range 0 to 2 pi, which you can see from this plot here. Okay, let's have a look at a dynamic plot here of that solution. First thing is, if I take Q down to 0, you'll see we do get just a cosine curve. Starts at the top here and oscillates 6 times over the range 0 to 2 pi. And similarly, if I push that back to where it started and bring this down to 0, you'll see I do just get a sine curve. Starts at 0, 0 and executes a classic sine wave 6 times over 0 to 2 pi. And as I start to alter P and Q, you'll notice two things change. Firstly, the amplitude of the motion changes. So it gets bigger or smaller depending on the absolute sizes of P and Q. And also you'll notice that the wave is being translated either to the left or to the right along the graph as that happens. And this is always a sine curve, and notice it's always a sine type curve with a 6x in it. So it's always oscillating 6 times. The next and final video in this sequence is 1.7 auxiliary equation with complex roots.